A 1 kilogram mass is attached to a 2 kilogram mass by a massless inextensible string. The system is on a perfectly smooth pulley. It is clear that if the system is released from this position, that the 2 kilogram mass will move downwards and the 1 kilogram mass will move upwards. Now, because we are assuming that the pulley is perfectly smooth, it will not rotate. The string cannot apply a force on the pulley in a direction along the circumference of the pulley, because the pulley is perfectly smooth, so the string cannot push on the pulley, if you like, in a direction along the string. Obviously this is the ideal situation. In reality a pulley would rotate to some extent. Let's look at the forces on the 1 kilogram mass. Obviously we have the weight of the 1 kilogram mass, which is 1 times g newtons. Now clearly there's an upwards force on the 1 kilogram mass because it's attached to a string. It should also be clear that this upwards force on the 1 kilogram mass has greater magnitude than the weight of the 1 kilogram mass, since we know that the 1 kilogram mass accelerates upwards. Let's say that the magnitude of this force is T. So we will be getting this force, upwards force on the 1 kilogram mass. Now let's look at the 2 kilogram mass. Well, its mass is twice the 1 kilogram mass, so its weight is double. Its weight is 2g. And since we know that it accelerates downwards, there must be an upwards force on the 2 kilogram mass that is less than the weight, 2g. Now it turns out that this upwards force on the 2 kilogram mass has the same magnitude as this force over here, and that's something that we will prove. Let's call this force, let's say the magnitude of this force is r. Now to show that these two forces have the same magnitude, we will consider the forces on the string. So here we're showing the forces on the masses. Okay, so here I'm showing the string again, and we apply Newton's third law to this part of the string. So we can see that the force on the 1 kilogram mass due to the string is T. So by Newton's third law, the force on the string due to the 1 kilogram mass is equal but opposite. So this vector has the same magnitude as this vector, so it's also T. Similarly for the other side of the string. Okay, the force on the 2 kilogram mass due to the string is R. So by Newton's third law, the force on the string due to the 2 kilogram mass also has magnitude R, but points in the opposite direction. Let's call the acceleration of the system A. Now it's clear that the 2 kilogram mass will accelerate downwards. So initially both of these are at rest and then they are released. So the string, the right side of the string will accelerate downwards with acceleration A, and the left side will accelerate upwards with the same acceleration A, because the string is inextensible, it cannot be extended. So all parts of the string, and indeed both masses, will have the same acceleration. Next we will look at the resultant force on the string along the string. So what are the forces on the string along the string? Well, these are the only two forces on the string along the direction of the string. Of course, there is another force on the string due to it being in contact with this pulley. At every point where the string is in contact with the pulley, we have a force on the string that's perpendicular to the string. So we have a force at that point and we have a force at this point. But these forces are not along the string, they're perpendicular to the string, so we forget about those forces. Now we also have the weight of the string, but we are assuming that the mass of the string is 0, which means that its weight is mg. Well, that's going to be 0 times g. If its mass is 0, its weight is obviously 0. So the only two forces to consider along the string are both T and R. Also we don't have any friction forces along the string because this pulley is perfectly smooth. Okay, so let's say F is the resultant force on the string along the string. Now we will take vectors pointing along this direction of the string, that's clockwise if you like, as being positive vectors. So we're dealing with vectors in one dimension really, but that that line is curving on itself. So any vectors pointing along this direction here are positive. So vector r is positive. But this vector here is negative. So the resultant force on the string along the string is r minus t. And by Newton's second law, that's equal to the mass of the string times the acceleration of the string. But we assume that the mass of the string is 0. Well, the mass of the string is so small that we can neglect it, in particular compared to the masses that are attached to it. So basically we're putting 0 in for the mass of the string. So we see that r minus t is 0a, which is 0, and from this we see that r is equal to t. So if the mass is negligible, we can say that these two forces have the same magnitude. Okay, so now let's calculate the acceleration of the system and also these two forces, tension forces on the masses. Well, one way we could do that is look at each mass. So we can start with the 1 kilogram mass. And we're going to take directions that go clockwise around the pulley as being positive. We could take the reverse direction, the anti-clockwise direction is positive. It doesn't actually matter. It's a little bit easier here because we know that this is the direction of the acceleration. So let's write down the force on the 1 kilogram mass. I'll just call that F1. Okay, so this vector is positive because it's pointing in the clockwise direction around the pulley, and this force is negative. So this is the resultant force on the 1 kilogram mass, and by Newton's second law that's equal to the mass of it, which is 1, times its acceleration, which is a. Now for the 2 kilogram mass, we see that the 2g force is pointing in the positive direction, but this force here is actually negative. So even though these two forces have the same magnitude, they have different directions using our convention here. They both point vertically up, but we're not taking up or down as our direction. We're taking directions clockwise around the pulley. So we're dealing with vectors in one dimension, but that dimension is not the up-down direction. It's actually the clockwise direction around the pulley. So these two vectors are actually different. This one is plus t, whereas this one is actually minus t. Okay, we apply Newton's second law, so the resultant force is the mass, which is 2, by the acceleration. So the key point here is that both of these accelerations are the same. So that enables us to solve for the acceleration. So if we simply add these equations together, we get the acceleration. If we add the left hand side, you can see the t's cancel. We have 2g minus 1g is 1g, and over here we get 3a. So we see that a is 1/3 g. Now of course we expect to get an answer that's less than g. G is the acceleration due to gravity when both masses are free to fall. Both of them would have the same acceleration, g. But since they're connected in this way, the acceleration we get is less than the acceleration due to gravity. Now we could have arrived at this answer by considering the system as a whole. So the system consists of the two particles and a string. So what are the forces on the system? Well, these two forces are internal forces on the system. So we could ignore these forces. We're only interested in external forces on the system, and the external forces are the weights of these two particles. So the resultant force on the system along the string is 2g minus 1g, and if we apply Newton's second law, we put the resultant force along the string equal to the mass of the system, which is the sum of these two masses, that's 2 plus 1, which is 3, times the acceleration of the system, which is a. So we get the same equation as we got up here. Now let's calculate t. So I've just subbed into the first equation. T equals 1 plus g, A plus g, where a is a third g, so we get t equals 4 thirds g. Okay, so let's look at the system. You can see that 4 thirds g is greater than 1g, and that's exactly what we want, because the 1 kilogram mass is going to accelerate upwards. The resultant force on the 1 kilogram mass is in the upwards direction. It's 4 thirds g minus 1g, which is 1 third g. So that's the resultant force on the 1 kilogram mass. Now over here we can see that the weight of the 2 kilogram mass, 2g, is greater than 4 thirds g, and that's exactly what we need. So the resultant force is downwards. It's 2g minus 4 thirds g. That's 2 thirds g. Now let's consider the general case of two masses m1 and m2. Now we don't know what's going to happen here. We don't know which direction each of these masses will accelerate in, so we'll just make up a direction. So let's suppose that this is the direction. So this is the positive direction. So vectors pointing clockwise around the pulley are positive. So the acceleration, let's say, is in the positive direction. So here are the forces on each mass. So the force on the first mass is T minus m1g by Newton's second law. That's its mass by the acceleration a. And the forces on the second mass are m2g minus t by Newton's second law. That's equal to its mass m2 times the acceleration a. So same acceleration in both cases, so we can solve these equations. We have two equations with two unknowns. We simply add them together, t's will cancel, and if I factorize out that g, this is what we get. And I can add these and factorize out a. Now again, like before, we could have arrived at this equation by considering the system as a whole. So we take the forces along the string, and the external forces on the string along the string are the weights m2g and m1g. That's the weights of the particles. The string is assumed to have no weight. So here's the resultant external force on the string along the string. Obviously there's a force on the string due to the pulley, but we're not interested in that force because that force is perpendicular to the string. It's not along the string. We have these two forces acting along the string, but they're internal forces. If we were to put these into this, they would just cancel out. We get plus t minus t, so as we've seen before, they don't come into this. They're not external forces. Okay, so by Newton's second law we set that equal to the mass of the system by the acceleration. Now the mass of the system is the sum of the masses of the particles, because the string has no mass. So we get the same equation as this one here. Okay, so here we have a general formula for the acceleration of the system. So to see that this formula makes sense, let's consider some examples. Let's suppose that the two masses are the same, m1 equals m2. Well, then the numerator up here will be 0, so we'll end up with a equals 0g, which is 0. So that makes sense. If the two masses are the same, we have no acceleration. You can also see that if m2 is greater than m1, then the acceleration will be positive. m2 minus m1 will be positive, and that makes sense because we're taking directions down this way, clockwise, as being positive. And similarly, if m1 is less than m2, then a will be negative. The system will move in the opposite direction to the convention shown. Also note what happens if m1 is 0. If we put 0 in for m1, we get a equals m2 over m2 times g. That's just 1g, so a will equal g. So that makes sense. So if this mass is 0, well, m2 will fall with acceleration equal to the acceleration due to gravity. Basically we have free fall for mass m2. Okay, in this problem we want to get the accelerations of both of these masses. Here are the weights of both of these masses. The force on both of these masses due to the string are the same. Well, they have the same magnitude, which I'll call T. We saw that these two forces have the same magnitude if the string's mass is essentially 0 and if we're dealing with a smooth pulley. So the string just glides over the pulley and the pulley does not turn in the ideal situation of no friction. it is clear that the 0.5 kilogram mass will move down while the 0.4 kilogram mass will move up. So the accelerations are known. The direction of the accelerations is known. So to make life a little easier, we will take that direction to be the positive direction. So vectors going clockwise around this string are positive. Vectors pointing anti-clockwise around the string are negative. So here is the resultant force on the 0.4 kilogram mass. And by Newton's second law, the resultant force is the mass, which is 0.4 times the acceleration, a. Here is the force on the 0.5 kilogram mass. So the 0.5 g vector is in the positive direction, whereas t is in the negative direction. So this vector is minus t. By Newton's second law, the resultant force on this mass is ma, where m is 0.5. So as we saw in the previous video, if we add the left-hand sides, the t's cancel. And from this, we find the acceleration of the system. Of course, it has to come out to be less than g. Of course, as we saw in the previous video, we could also consider the system as a whole. So we could just look at the one-dimensional situation. So the system has just one dimension. And look at the external forces acting on the system. So I could show the system like this. So if we take directions to the right as being positive, well, the resultant force on the system is 0.5g minus 0.4g. We can forget about the two tension forces. I can put them in if I want, but if we sum the four forces, these two tension forces will add to 0. And besides, these are internal forces, so they're not responsible for accelerating the system. So the system consists of the two masses and the massless string. Okay, so we could imagine applying Newton's second law, get the resultant force, and that must equal mass times acceleration. Well, the mass of the system is 0.5 plus 0.4. Okay, if we take the system as a whole, that's 0.9, and the acceleration of the system is a. So as before, we get a equals 1/9 g. After falling 1 meter, the 0.5 kilogram mass strikes a horizontal surface and is brought to rest. The string again becomes taut after t seconds. Okay, we want to find how long it takes the string to become taut. That is after the string has become slack. So while the 0.5 kilogram mass is moving down, the string is taut. So we are going to be interested in the velocity of this mass just before it strikes the ground. And that's going to be the same as the velocity of the speed of the 0.4 kilogram mass just before the 0.5 kilogram mass strikes the ground. If we know the speed of this, we can then consider what happens after this mass has struck the ground. So initially, the 0.5 kilogram mass was up around here. Its speed was 0. We know its acceleration. We just worked it out. It's 1/9 g. The distance it travels is 1 meter, and we want its velocity just before it strikes the ground. Okay, so straightforward problem, uniform linear motion. Acceleration is uniform. Okay, so now we have this speed of this particle just before the 0.5 kilogram mass strikes the ground. Particles are connected with an inextensible string, so they have the same speeds at each instant. Okay, so this mass's initial velocity will be √2/9 g upwards. And of course it's going to move up for a certain amount of time, so the string will become slack and it'll reach a maximum height and then fall back down again to its position. So while the string is slack, what are the forces acting on this mass? Well, clearly the only force acting is force of gravity, which we know is mg, 0.4 times g. Of course, for the motion of this particle, we only need to know its acceleration, and the acceleration of all masses is just g. If we set this equal to ma by Newton's second law, ma is the resultant force. It's the only force acting on it after the string becomes slack. Then, we just cancel the masses. It doesn't matter what the mass is. We know that the acceleration is g. So we don't want the force on it, force of gravity on it. We just want the acceleration vector. So the acceleration vector is downwards, and its magnitude is 9.81. So one way to do this problem is to find the time taken for it to reach its maximum height. When it reaches its maximum height, its velocity will be 0. So we know its velocity is decreasing by 9.81 meters per second each second. And it'll decrease to 0, and then the velocity downwards will increase to what it was originally. So when it gets back down to its original position, just before the string becomes taut again, its velocity downwards, well, we won't call it u, but its velocity downwards will be root 2/9 g. So the time it takes to reach its maximum height and the time to fall back down from its maximum height to its original position are the same. Okay, so I'll find that time. So at t equals 0, the particle is here, just before the string becomes slack. The particle has inertia. It wants to move in the upwards direction. And at t equals sometime t later, its speed is 0. So if upwards is positive, we can see the acceleration is negative. So from v equals u plus at, we can find that time. So solving, we get 0.1505 seconds, and we want to double that because the time taken to go up is the same as the time taken for the particle to fall back down again. In other words, the time for the particle's speed to go from root 2/9 g to 0 is the same as the time for it to drop from 0 to minus root 2/9 g. That's because we're dealing with uniform acceleration. Just a small point here, that time is referred to as t. It's called half the time t, but of course that doesn't matter. We found the amount of time that the string is slack.